Então, você está com a palavra, Marcos.
Okay, thank you. Welcome, everyone. Good afternoon. Today we have a talk by Tiago Fonseca, but before that, I'd like to share this very sad news that last week our colleague Fernando Torres passed away on May 28th in the morning. And I would like us to observe 1 minute of silence in honor of Fernando. Okay, thank you, everyone. So it's my pleasure to introduce Tiago Fonseca, who will talk about from transcendental numbers to higher Ramanujan equations. So please, Tiago, go ahead. So unmute yourself.
Yeah, thank you. Can you all see my screen?
Yes, we do.
Yes, presentation. All right, so thank you very much for the invitation. I should say it's a real pleasure to speak in this seminar. And I can also see that some teachers of mine are present, teachers of when I was an undergrad. So I hope you will enjoy the talk. All right, so I should say that I was very much inspired by George's talk last week. So I decided to do some kind of historical introduction too. So let's start right away. So I wanted to start with something everyone understands, a circle. So this is the circle. We all know it has this very nice algebraic equation. And we also know that this geometrical shape in some sense corresponds to a number, a very special number in mathematics, which is the number pi. And pi is basically given, well, I mean, you find this number when you try to compute, for instance, the length of this curve. And so here's a way of expressing pi. But if you try to get your hands at this number, you quickly realize that it's actually quite complicated. You start to realize that it's not rational, and even worse, it doesn't look like it's an algebraic number. So it's not a root of any algebraic equation with rational coefficients. So for a long time, it was a real problem to prove that. I mean, is this number transcendental or not? Until Lindemann, in this very important paper, proved that indeed pi is transcendental, thereby solving very old Greek problems on the squaring the circle. And there you go. Now, of course, we can sort of play the game with other shapes. So there are other interesting curves that appear naturally. So here's another one. So this is the lemniscate, this very beautiful shape here. which also has a nice algebraic equation. And this curve occupies a very important place in the story of mathematics, in the history of mathematics, because it's related to elliptic integrals. Okay, so if you try to do the same thing here, try to compute the length of this curve, you stumble upon some elliptic integral. And so you find this number that I call omega, which is given by an integral like this, which is sort of the analog of pi, but for this lemniscate here. And again, this number was very much studied along the history of mathematics. Some people call it the Gauss constant. Gauss also studied a lot this number. You can, so it's given by this integral, which is basically this arc length here. But using formulas involving the gamma function, you can also find other expressions for this number. For instance, this one. And then you can sort of ask the same question: is this number algebraic? Doesn't look like, but then you have to prove this. And well, much later, this was proved by Schneider in the 30s, already in the last century. And the proof goes by studying elliptic functions. Okay, now here's another question. So you have this pi, you have this omega. I mean, is this really a new transcendental number? So we have the feeling that omega cannot be something related to pi, kind of because the circle has a very different geometry from this curve here. But you can try to phrase this problem precisely. So the way to do this algebraically is to ask if omega is algebraically independent to pi. So this means that, I mean, that there's no polynomial in two variables with rational coefficients that has omega and pi as a root. Okay, so what is the answer to that question? Well, then much later, this was proved by Nevskys that these numbers are actually algebraically independent. So this is the ICM proceedings paper. And he actually proved much more, and I will discuss this later in this talk. But his proof also goes by studying elliptic functions. Okay. Now, just to show you that very quickly you reach to things we don't know the answer. So a problem in the same spirit. So pi being algebraically independent to omega is the same thing as pi being algebraically independent to gamma of 1/4 because of that formula I had before. And now you also have other independence conjectures on values of the gamma function. So this one, for instance, we don't know how to solve yet. Now, it's you can say that this. I mean, how do you come up with this kind of problems? So for a lot of people, transcendence theory has this reputation of being a very hard and difficult domain of mathematics, but also of being in some sense esoteric, in the sense that you don't understand where things are coming from, and there's not a lot of structure. So what I want to explain now is I want to say that there is order in chaos, and the key to understand that is algebraic geometry. And I want to show that if you look at these problems under the right point of view, the statements make a lot of sense and become even natural. Okay, So that's what I want to do now. It's still part of the motivation of the talk. And this, for this, we have to go back 10 years from that paper of Nevsky to this wonderful paper of Grynzik on the Durand cohomology of algebraic varieties. And so I invite everyone to read this paper if you've never done it before, because it's written in a very informal style, because it was a letter Grynzik. It's part of a letter Grynzik wrote to Atiyah. And so let me explain briefly what this paper is doing. So the idea is the following. So let's start with some smooth algebraic variety over Q, okay, over the rational numbers. Now, you can certainly compute you can consider the C points of this algebraic variety, and then you will get some complex manifold. And then you compute the singular homology, take the dual, you have a singular cohomology. Here I'm considering with coefficients in Q. So it's some Q vector space that you compute by going to this associated complex manifold. And people in arithmetic geometry usually call this Betti cohomology. But what Grynzik showed in this paper is that there's another cohomology theory, which is purely algebraic, and also computes, in some sense, the same cohomology group. And so it's this algebraic Durand cohomology, which is defined using only algebraic differential forms. And so the definition is just that this cohomology group here is the hypercohomology of this complex of algebraic differential forms. And this is also a Q vector space here, because a variety is defined over Q. So from this smooth algebraic variety defined over Q, you can consider two cohomology groups, which are two different two Q vector spaces that are the same if you complexify everything. So and that's what he proves here, is that this algebraic Durand cohomology, if you complexify, you're really computing what you expect. And so this usual map that associates a differential form to integration along cycles gives you an isomorphism between the complexification of these two cohomology groups. And in arithmetic geometry, you usually call this a comparison isomorphism. Okay, but now another way of looking at this, at what is happening, is that essentially you have this one cohomology group, complex cohomology group, that has two a priori different Q structures. So there are two Q vector spaces whose that if you tensor with C, you recover this original complex cohomology. Now, what is measuring the difference between these two Q structures are what we call nowadays periods. So periods, of course, it's a very old thing in mathematics, but let's say in the more modern terminology would be integrals of algebraic differential forms defined over Q over Q rational cycles. Okay, and so if you write the base change matrix for this comparison isomorphism by choosing some bases here in the Durand cohomology defined over Q and some bases in the Betti cohomology also defined over Q, you get this matrix of complex numbers, and they somehow are measuring how these two Q structures are different. Okay. Now, I had other examples in a previous version of these slides, but I cut them off. So let me go straightly to the case of elliptic curves, which is again very classical. So let's consider an elliptic curve given by this classical Weierstrass equation. Okay. But I'm going to take U and V defined over Q. And this condition just ensures that this is non-singular. Then, to compute the algebraic theorem cohomology, there are different ways of doing that. One of the things you can do is to show that the algebraic theorem cohomology, the H1 of this elliptic curve, is the same thing as the H1 of the affine elliptic curve, which is just the elliptic curve minus the point at infinity. And the theorem cohomology of affine schemes is easier to compute. Is just the actual cohomology of the complex of algebraic differential forms. And so you do this computation and you recover this, which is again classical in some sense. That this theorem cohomology is two-dimensional, generated by these two classes here. So this, in the classical terminology, is the form of the first kind, and this is the form of the second kind. There you go. And well, the Betti cohomology we understand very well because the complex points of this give a torus. And then you can choose like this cycles here, this gamma 1, gamma 2, and then you can form this period matrix, which is classically denoted like this. So and so classically, these guys, omega 1 and omega 2, which are the integrals of this form of the first kind, are what are called periods in the classical terminology. And this eta 1, eta 2, which are the integrals over this form of the second kind, are people call them quasi-periods. Okay, nowadays we just call everything periods. And so you got this 2x2 matrix. So these periods, of course, they're very important because they generate the lattice that uniformizes your elliptic curve in the complex picture. And then again, this is very classical. There's this Legendre period relation that says that if you choose well your gamma 1 and gamma 2 here, you get this relation between the periods. And just to come back to what I said in the beginning, if you consider the particular case where u is 4 and v is 0, so this particular elliptic curve, and then for an appropriate choice of gamma 1 and gamma 2, you can compute that omega 1 is this omega, this Gauss constant, and omega 2 is I times omega. Okay. All right, so this is just an example. Now, what is amazing about this framework is that is this remark here that you can see from this framework that algebraic cycles, in some sense, induce algebraic relations between periods. So let me explain this in a concrete situation, a very special situation. So take an elliptic curve again, and take some, and suppose it has complex multiplication. So there's some endomorphism, which is not just multiplication by some integer. Okay, and so this in this picture here would correspond to a certain one cycle in the product of the self product of the elliptic curve, which is just the graph of this endomorphism. Okay, now the point is that this comparison isomorphism, comparing these two cohomology theories, is canonical and functorial, and so it will commute with the natural maps that this endomorphism induce on cohomology. So this is the pullback in the run cohomology, and this is the pullback in Betti cohomology, and so it commutes. And then if you write in terms of matrices what this means, it gives you a relation like this. So here's this matrix defined over Q because you have this Betti cohomology defined over Q. Here you get 0 because this pullback here in the run cohomology must preserve the Hodge filtration, so must preserve the space generated by the form of the first kind, and so you can prove there's a 0 here. And then if you just look at this relation and divide the first entry by this entry, you get this classical statement here that the quotient of these two guys is an algebraic number, is actually a quadratic imaginary number. Okay. All right. Now, what Grothendieck conjectured is that actually this thing that algebraic cycles give relation between periods actually explains all the relations between these numbers. So I wrote here that every algebraic relation between periods is of motivic origin, just to be correct and vague at the same time. But that's what it's saying, that every algebraic relation between periods should come from some algebraic cycle in the self-product of the variety. And so here's a footnote on that article I mentioned, where he first states something in that direction, but not quite this statement. And now, the nice thing about this conjecture, which I won't really have time to explain here, is that you can reformulate it in as some transcendence statement. So basically, you start with some variety here, x, and then you consider the field generated by all the periods of x. So basically, the period generated, the field generated by the entries of that period matrix. And then the period conjecture is saying that the transcendence degree of this field should be equal to the dimension of some algebraic group, which is the motivic Galois group of this x here. So if you're familiar with Hodge theory, at least in the case of abelian varieties, you can take this motivic Galois group as a Mumford-Tate group. So it's essentially the group of endomorphism of your cohomology that preserve all Hodge cycles in algebraic constructions in this cohomology. Okay, but let me just say that there is some algebraic group that you can compute in some cases, and the period conjecture is actually just saying that you should have this equality here. Now this is very nice because it allows you to guess what should be true and what should not be true, at least. So for instance, for elliptic curves, you can compute this motivic Galois group, and you can show that it is two-dimensional if E has complex multiplication, and it's four-dimensional if not. So it says precisely what the transcendence degree of the field generated by all the periods should be. Okay, and then yeah, so in the CM case, this Nevskys theorem proves exactly the period conjecture for this CM elliptic curve. But in general, already for an elliptic curve that is not CM, it's open. Okay, now here's a more interesting example, a genus 2 curve. So let's consider this hyperelliptic curve given by this equation. So it's a very special curve. It's very symmetric in a sense that it has this automorphism here. Okay. So you can compute a basis of the Theorem cohomology given by differential forms like this. And if you think long enough, you can also compute an explicit basis of the Betti cohomology, which I will not make explicit here. And then you can compute the periods, and you get that the periods are given by this. So I wrote here in terms of the beta function, which is something involving the gamma function. So these are very classical quantities, integrals. And now these computations here say that the periods, the field generated by all the periods of this hyperelliptic curve, if you express this in terms of gamma functions, is contained in this field generated by pi gamma of 1/5 and gamma of 2/5, and that this extension here is algebraic. Okay. Very well. Now, you can also prove that the motivic Galois group of this curve here has dimension 3. So the period conjecture predicts that these numbers are algebraically independent. And that's how this statement, doesn't come out of the blue. It comes from this period conjecture. Okay. All right. But the problem is now, if you want to attack this problem, so this method of Nevskys actually proves something here. In this case, proves that at least 2 of these numbers are algebraically independent. But you cannot prove that all of them are algebraically independent. And in particular, you don't even know that gamma of 1/5 is transcendental, for instance. Now, is there another approach to this problem? So that's what I want to discuss in this talk. So in '96, Nestorenko published this remarkable theorem here. It says the following. Take any point in the Poincaré upper half plane, okay, and then compute these 4 numbers here. So this E2, E4, E6 are Eisenstein series. I'm gonna define them in a minute. And it says that among these 4 numbers, at least 3 of them are algebraically independent. This is what this means, okay? So it's a very strong result because it works for any point in the upper half plane. So these Eisenstein series are very important functions in number theory. So there are functions in this Poincaré upper half plane that are quasi-modular forms. In particular, they have some kind of Fourier expansion with integral coefficients, and that are given by these arithmetic functions here. So it's some kind of very special function in number theory. And the cool thing about this Eisenstein series is that actually, or of any quasi-modular form, is that their values compute elliptic periods. So the values of this Eisenstein series are actually periods of elliptic curves. So if you prove something about the transcendence of the values of these guys, you also prove something about the transcendence of periods of elliptic curves. And in this sense, you can prove that these formulas imply that Nestorenko's theorem actually improves the theorem of Nevskys because it has this extra thing here. And so if you set tau equals to I, for instance, you can prove that E6 of I is 0. And then you get that these 3 numbers here are algebraically independent. And you can compute them in terms of elliptic integrals. And then the conclusion is that e to the pi, and gamma of 1/4 are algebraically independent. And this, so this is very strong. So before Nestorenko, we didn't even know if pi and e to the pi were algebraically independent. So this is even stronger. And this is just one value, just one application of this theorem. Now, another remarkable thing about this theorem is that the proof never uses explicitly the fact that these functions are quasi-modular forms, so that they satisfy some modularity property. It relies actually on the fact that this series here have integral Fourier coefficients, and that they satisfy some system of differential equations, algebraic differential equations. And this is these are the Ramanujan differential equations that I put here. And so a very natural question is, well, can you generalize this picture? Because modular forms admit higher dimensional or analogs in several variables. So they have Ziegler modular forms, Hilbert modular forms, etc. So a very natural question is to try to generalize this method of Nestorenko to transcendence statements about these higher modular forms. And actually, people try to do that or have work in this direction. So here are just two examples of some work of Zudelin in the year 2000 in the context of theta functions, and the work of Pellerin 2004 in the context of Hilbert modular forms. But one quickly realizes that the differential equations that appear here in this case of modular forms of several variables are really very complicated if you look at them in this elementary way. And so perhaps one should approach this problem in a more geometric way, in which you don't really need to rely very explicitly on the form of the equation, but just on the geometric properties it satisfies. And so that's what I want to explain now. Is this geometric approach, which was initially inspired by Movasati's reinterpretation of the Ramanujan differential equations in terms of some vector field living in some moduli space. So here's the generalization I want to talk about today. So we will consider an arbitrary base field K, and then we will deal with principally polarized abelian varieties of dimension D defined over this K. Okay, so so if you take G equals 2, this is just you can just think about Jacobians of genus 2 curves, but you can also think more generally about this picture. And the case G equals 1 corresponds to the case of elliptic curves, because elliptic curves have a canonical principal polarization. Now, given an abelian variety like this, we can consider its algebraic theorem homology that I recalled in the beginning. So this will be a 2G dimensional K vector space with two extra structures. So first of all, it comes for free with a symplectic K form. So this everything here is defined over K, which comes from this polarization here, and also comes with a Lagrangian subspace for this symplectic form, which is the Hodge filtration, which is simply given by regular or holomorphic forms in this theorem homology. But everything is defined over K. Now, with these two structures, I'll make just a definition to simplify. I'll say that a symplectic Hodge basis of this theorem homology is just the basis of this vector space. It comes in two parts like this, where the first part will be omegas will be a basis of this Hodge filtration, so this space of holomorphic forms. And I'll also require that the whole basis will be symplectic with respect to this symplectic form. Okay. Now, in the case of elliptic curves, the basis I showed you in the example is an example of symplectic Hodge basis. You can compute that this pairing between these two forms is equal to 1. This is holomorphic, so this is a symplectic Hodge basis. All right. Now, given this definition, what we are going to consider is a moduli space classifying such objects. So, so I put here the precise terminology, but I hope this will not scare people. So BG will be the moduli stack, or the moduli space, if you prefer, classifying principally polarized abelian varieties of dimension G, equipped with a symplectic Hodge basis. Okay, and then this is characteristic free, and it's even better than characteristic free. It works over Z, so that's why I'm considering this moduli stack over Z. And this will be smooth, and it's a very well behaved kind of stack. Is a Deligne-Mumford stack. Okay. And we can prove that if you base change to z of 1/2, so if you invert the prime 2, this already becomes representable by a smooth quasi-affine scheme that I call BG, like straight BG. And this is the dimension of this scheme. Okay, just the same dimension of the symplectic group. Okay, so you have this moduli space. So in the case of elliptic curves, it's not very difficult to compute that explicitly. And what you get, first of all, it has dimension 3, which is good, because it should, in some sense, be related to these Ramanujan differential equations, which are 3-dimensional. And then you can prove that if you work over this ring here, you can identify this moduli space with this very simple open subset of an affine 3 space, given just by inverting the this discriminant here. Okay, it's something you can compute explicitly. Okay, now what I want to explain now is how you can define over this moduli space, in some sense, a canonical family of vector fields that will generalize these Ramanujan equations. Okay, so to explain that, let me first give this picture here. So we have this moduli stack BG, okay, and we can just forget this basis of the theorem homology, and this will map to the moduli stack AG that classifies just principally polarized abelian varieties, okay, and I call this pi. Now you can see this as a principal PG bundle, where this PG is this parabolic subgroup of the symplectic group of degree 2G. And the reason is that basically if you act on this symplectic Hodge basis, if you want the result to be another symplectic Hodge basis, you are acting by an element of the symplectic group, but that should preserve this Hodge filtration, and that's why you get this parabolic group here. And this particular group is sometimes called in number theory the Ziegler parabolic subgroup. Okay, and so you can see this moduli stack as some principal bundle over the moduli stack of abelian varieties, principally polarized abelian varieties. Now, what I claim now is that, so you can consider this exact sequence here on the level of tangent bundles. And what I claim now is that there's a canonical splitting of this sequence. And so this splitting will give origin to some subbundle here, which will correspond to a horizontal foliation. Okay. So first things first. So let me explain how you get the splitting of the sequence. So the idea is the following. So let us consider the following vector bundle over AG, modular space of abelian varieties. So this will be simply the vector bundle whose fiber at a principally polarized abelian variety is this space given by G copies of the first theorem homology of the corresponding abelian variety. Okay. Now you make this vary, and you can prove that you get a nice algebraic vector bundle over this moduli stack. Okay. Now the point is that you can actually see this BG here inside this vector bundle. And the reason is that a symplectic Hodge basis is actually completely determined by the second part of the basis, so just by the eta 1 to eta G part. And so you define this map that associates this symplectic Hodge basis just to the second part, and you can prove that this is an immersion. It's not a closed or open immersion, it's a locally closed immersion. But the point is that you can see these inside this vector bundle. And now what we use is that this vector bundle actually comes for free with a connection. This is the Gauss-Manin connection, which essentially tells you how to differentiate the Ramanujan cohomology classes. Okay, so I won't have time to go into that, but there is a canonical connection on this vector bundle, and so a connection on the vector bundle gives a splitting of the corresponding sequence on the tangent bundles for this vector bundle here. Okay, which is just this famous Ehresmann point of view of connections. So in particular, it gives like this retraction here, which will give a splitting of this sequence. And now, because you can see BG inside this vector bundle, you can prove that this splitting here over this space actually induces a splitting over BG. So it will induce a splitting here of the original sequence. And therefore, you get some sub-bundle of the tangent bundle of BG, which you can prove it's integrable, which is isomorphic to this one. So it's a horizontal foliation. Okay. Now, if you don't know what a foliation is, it doesn't matter, because what I want to show now is that this picture is actually even nicer, because this subbundle here actually has a canonical trivialization. So I can find vector fields that give a frame for this bundle here. So how does this go? Well, so here's the idea. So consider this other vector bundle over AG. So it's this sometimes called the Hodge bundle for AG, whose fiber at over an abelian variety, so a point at in the modular space, is just this space of holomorphic forms. Okay. Now the Kodaira-Spencer map, this usual Kodaira-Spencer in deformation theory, in the case of abelian varieties, acquires a very special form. It allows you to identify the tangent bundle of this moduli stack with the dual of the second symmetric power of this vector bundle here. Okay, but now because we have this isomorphism here on the pullback to G, when you pull back this thing to G, so this F is just given by holomorphic forms, and BG classifies abelian varieties with a trivialization in the Ramanujan cohomology, but in particular also a trivialization on the space of holomorphic forms. So this pullback of F to BG is canonically trivialized, and so you can canonically trivialize the pullback of that, but the pullback of that is isomorphic to by Kodaira-Spencer to the pullback of the tangent bundle of AG. It is isomorphic to this foliation here, to this sub-bundle we defined before. And so this gives a canonical trivialization of this vector bundle here. And these are the higher Ramanujan vector fields. Okay, so there are other ways of defining these vector fields, but I just wanted to show that actually, I mean, everything is given from the very definition of this moduli space. Okay. Now, again, in the case of G equals 1, you can compute this very explicitly, and it's not very difficult. And you can show that you recover. So in this case, there will be just one vector field, and you recover this vector field associated to Ramanujan's differential equations. Okay, which is what Movazati did originally. Okay. Now, here I will not go into details, but okay, so you have this family of vector fields, but you can also show that you have some solution of the differential equations defined by these vector fields. And this solution is parametrized in this Zigel upper half space, which is some higher dimensional generalization of the Poincare upper half plane. Okay, so it's given by symmetric matrices with a positive definite imaginary part. And so we can also construct a holomorphic map that goes from the Zigel half space here to the C points of this modular stack, which is just a complex manifold because it is representable. And we can show this has Fourier coefficients defined over Z in some sense. So it's very much like this E2, E4, E6, this Eisenstein series. And that this satisfies the corresponding differential equations. And so this is what I call the higher Ramanujan equations. Okay. So again, this precisely you can prove that this generalizes this picture you had for elliptic curves. So so phi 1, if you set g equals 1, you get E2, E4, E6. Okay, so this is some generalization of this system of differential equations. And now, of course, the question is, what can you do with that? Okay. Now, there's already one nice thing here that that indicates that this is in the right way. This generalization is something that is in the right way, which is the fact that we can actually prove that the values of this map, this solution of the differential equations. So so here you should either interpret this as given by the field of definition of the corresponding point on the complex manifold, or you can say that this space is quasi-affine, and then you choose coordinates, and then you take really, so this would be really numbers. So you can prove that these values are actually periods of abelian varieties. So as before, we had that the values of Eisenstein series are periods of elliptic curves. You can prove that values of these guys here are periods of abelian varieties in this sense, in this very arithmetic sense that I explained in the beginning. Okay, and actually the statement is actually much more precise than that. In some sense, this 2 pi I tau and the image of this phi g of tau, which lives in the Zigel upper half plane, actually computes the whole field of periods of an abelian variety up to a finite extension. But if you're interested in transcendence, this finite extension doesn't play any role. Okay, so this is saying in particular that for any abelian variety, so for any principally polarized abelian variety, you can recover its periods as some value of this phi g at some point. Okay. So this is saying that, well, now this is precisely saying that if you somehow you can extend Mr. Enkel's methods to these guys, to these generalizations, you will end up proving results on periods of abelian varieties. Okay, so for instance, if you can do that for g equals 2, by what I explained in the beginning, we will be able to prove the algebraic independence of these 3 numbers here, because they are related to the periods of a genus 2 curve, or of its Jacobian, which is the same thing. Okay. Now, okay, so what can we do? So one thing I would like to remark already is that so the period conjecture is dictates what should be true and what should not be true, right? So here's, for instance, one consequence of the period conjecture, if we knew it was true. So the point is that generically you can prove that this motivic Galois group, or this Montfort group, will be equal to the general symplectic group of order 2G. So you know that generically, for a generic abelian variety, this will have this dimension here. And so using that, if you think a little bit, you can conclude that the period conjecture is saying, for instance, that the image of this phi g, because of this theorem here, should be Zariski dense in this space. Okay. So in the case of in the usual case, this corresponds to saying that E2, E4, E6 are algebraically independent as functions. And this kind of statement is actually important in Nestorenko's transcendence method, or in general transcendence methods. You usually have to prove some kind of functional statement too. And so here's we can prove actually something stronger in this case here. So we can prove that every analytic leaf of this foliation defined by the Ramanujan vector fields is Zariski dense in this space. And this property, this stronger property, actually for G equals 1 plays the corresponding property for G equals 1 plays an important role in Nestorenko's proof. So this is some kind of thing you expect to recover in this general picture, and whatever transcendence method, if you can get one, you definitely have to use that somewhere. Okay. But the nice thing about this geometric description is that it's actually not so hard to prove this theorem once you understand the geometry of this. So let me just explain very briefly how you prove this in the special case for the special leaf here for this image of T. So this solution of the higher Ramanujan equations. So the idea is that it suffices to prove that this guy here is Zariski dense in each fiber of this pi map that I defined before. Well, this moduli stack of abelian varieties is given by the quotient. So here is an orbifold quotient of the Zigio upper half space by the action of the symplectic group with integral entries. Okay, and so to give a point here, it suffices to give some point in the upper half space. So I fix some point, and then I look to the fiber that this point here defines, and I intersect this with this set here. Now, as I said, this is some kind of principal bundle under this group PG. So you can see the intersection of this fiber with this guy as some subset of PG of C. And this is precisely the subset you get. And then you get some explicit matrices here. So tau is fixed. What is varying is this ABCD in the symplectic group over Z. And then you only have to prove that this is Zariski dense here. And this follows very easily from the fact that SP2G of Z is Zariski dense in SP2G of C. And then for the general case, you just use that you can get the other leaves of this foliation by acting through the symplectic group. Okay. Now to conclude, so this is my last slide. I just wanted to mention this. So I explained that the image of phi g is Zariski dense can actually prove something a little bit stronger, that the graph of phi g is Zariski dense in this space here. So this is just symmetric matrices of order G. This is the moduli stack G, and so this is Zariski dense here. Okay, and these actually, if you translate this back in terms of periods, is proving something. You can interpret these results in some interesting way. So let me go back to this footnote of Grothendieck, and let me just read something here. So he recalls this algebraic relation between periods of elliptic curves, this Legendre period relation that I explained before, and he says that this is the only known general algebraic relation among these two numbers, and that so he expects this to be the only general algebraic relation. So the only algebraic relation that is satisfied by the periods of any elliptic curve. Okay. Well, you can make this precise, but this statement is generalizing this to abelian varieties. This statement that the only general algebraic relation between periods of principally polarized abelian varieties are the periods relations given by this polarization data. As I explained, that cycles give period relations, and this polarization gives some cycles, so they give some relations, which have to do with the fact that these period matrices live in some general symplectic group. But then this statement here is saying that these are the only general relations that these periods should satisfy. I think I'll stop here.
Thank you very much, Tiago. Are there any questions?
I have one. So what is missing to do Nestorenko and Genus 2?
A lot. So yeah, of course, I didn't explain what actually goes into the method, but usually a transcendence theorem will rely on some growth condition. This is somehow okay, but also it should rely on what people call zero estimates. So so you want to bound. So in the case of in the usual case, E2, E4, E6, you want to bound. You take, let's say, a polynomial in 4 variables, and you want to bound the multiplicity at 0 of this polynomial composed with Q, E2 of Q, E4 of Q, E6 of Q. And you need to prove that you have some good bound of that. And this is very hard to prove. And there's not much work on this kind of statements in several variables. And I would say this is the main obstruction to getting a statement like this kind of zero estimates. And there's another obstruction, which is the fact something you do not see in the one-dimensional picture, which is the fact that now this higher dimensional picture, so these moduli spaces, they have special subvarieties. And so in the Nestorenko theorem, you have this uniform bound on the transcendence degree, and you don't expect that in this higher dimensional picture, because this special subvarieties they should behave differently. But this kind of says that if you hope to attack this problem, you should adopt a more geometric point of view, because you will never be able to see this just working with formulas, because somehow in your method you have to take into account this special subvariety.
Okay, thank you.
More questions?
Yeah.
If not, let us thank Tiago again. Very nice to have Tiago giving this talk here, all the way from England. And I remind everyone that there's been a change in the program for next week. Next week, we're going to have a series of